Good day everyone, my name is Tanipin and I will be presenting our program for CST435 Parallel and Cloud Computing. Our program focuses on implementing a parallel image processing system using Python, where we compare two different parallel programming approaches which are multiprocessing and multi-threading. First, I will explain how our program is organized and how each file works together. Our program uses a modular structure where data, logic and execution script are separated. So, here listed out all our program files. First, for the input image folder, this folder stores all input images using for testing. The images are taken from the Food 101 dataset and prepared using setup dataset Python file. The next one is filter Python file. This file is the core processing module. It contains functions to load and save images. It also implements all filters such as grayscale, blur, edge detection, sharpening, and brightness adjustment. Next one is setup dataset Python file. This script prepares our dataset. It downloads the Food 101 dataset using KK Then it will randomly select a specific number of images based on user input. Next, the main multiprocessing Python file. This script implements the process-based parallelism. It uses multiprocessing pool to create multiple processes, and each process works independently and bypasses Python's GIL. The next one is the main concurrent Python file. This script implements the thread-based parallelism, and it uses the thread pool executor to manage multiple threads, and the threads will share the same memory space. Next is the benchmark Python file. This script automates our performance testing, and it runs both multiprocessing and multi-threading script. It will test different worker counts which are 1, 2, 4, 8, and 12. It will calculate execution time, speed up, and efficiency. Last but not least is the requirement text file and the README file. It will list all the required libraries such as NumPy, OpenCV, and KK and provide installation step and usage instruction. The last two one is output concurrent and output processing file. These two folders will store the image processed by using the multi-threading and multi-processing. All output generated by main concurrent Python file and the main multi-processing Python file. So you can see that before running our program, the output concurrent file will be empty. And this will then apply to the output multiprocessing folder.
My name is Angeline. I'll be presenting the performance comparison and analysis for multiprocessing and multi-threading. First is to compare the execution time analysis when using 4 virtual CPU cores on 5,000 images. So from the graph, we can see that the fastest execution time for both multiprocessing and multi-threading is when the worker count is set to 4. The execution time decreases, which means it is faster when the number of workers increase from 1 to 4 for both multiprocessing and multi-threading. So at 1 worker, both methods have nearly the same execution time because they are doing sequential execution with no parallelism. While at 2 workers, the execution time is reduced by about half as they are using the 2 physical CPU cores effectively to do parallelism. The best performance is achieved at the 4 workers, where all available virtual CPUs, including the hyper-threaded cores, are utilized. However, if you notice, the performance gain from increasing the worker count from 2 to 4 is smaller than the gain from 1 to 2 workers. So this is because the hyper-threaded cores do not provide the same performance as physical cores. Overall, the multiprocessing performs slightly better than the multi-threading because it avoids the Python's global interpreter lock, which is GIL, and enables the true parallel execution. Besides, we also run the processes using 8 virtual CPU cores on the virtual machine. So from the graph, we can see that as compared to the 4-core setup, the 8-core instance provide higher computational capacity and better scalability. The scenario is actually quite similar to the 4-core virtual CPU. So at one worker, both of the paradigms have nearly the similar execution time as they are doing sequential execution. Execution time decreases almost proportionally when increasing the workers from 2 to 4 because it is using the 4 physical CPU cores for parallelism. For 8-core, the lowest execution times are achieved at 8 workers. So at 12 workers, the multi-threading performance degrades, while the multi-processing performance remains stable. As overall, the multiprocessing is still performing better than the multi-threading. The performance improvement becomes smaller at higher worker counts because the hyper-threaded cores are less effective than physical cores for CPU-intensive tasks. Next, we look at the speed-up analysis. So speed-up is used to measure how much faster the program can run when using multiple workers compared to a single worker, which means to measure how much parallel execution improves the performance as compared to sequential execution. For 4 virtual CPU, the highest speed-up is when using 4 workers, while in 8 virtual CPU configurations, the highest speed-up is at 8 workers. With 1 worker, the speed-up is 1 for all cases as it is serving as the baseline. While for the 8 virtual CPU configuration, we can see that the speed-up scales better, reaching about 3.9 at 4 workers and nearly 5 at 8 workers. While at 2 workers, the speed-up nearly doubles in both configurations because parallel execution happens in 2 physical CPU cores. For the 4 virtual CPU configuration, the performance does not reach the ideal speed-up of 4. This is because of the limited benefits from hyperthreading. From this analysis, we can know that speed-up increases as the number of workers increases for both of the scenarios. Overall, multiprocessing achieves slightly higher speed-up than the multi-threading, especially at the higher worker counts. So these results highlights the importance of matching the number of workers to available CPU cores so that it can achieve optimal parallel performance. Next, we look at the efficiency analysis. So efficiency is used to evaluate how effectively the CPU cores are utilized as the number of workers increase during the parallel execution. For both configurations, the efficiency is 1 at 1 worker as it is executing sequentially. At 2 workers, the efficiency remains very high in both setups. For virtual CPU configuration, the efficiency drops at 4 workers and continues to drop at 8 and 12 workers as the system begins to rely on the hyper-threaded cores. So this is because at high worker counts, most of the workers contribute little to the performance improvement. In 8 virtual CPU configuration, the efficiency remains high up to 4 workers. At 8 workers, the efficiency started to decrease as the hyper-threaded cores are used, but it still remains higher than in the 4 virtual CPU case. Overall, the 8 virtual CPU configuration maintains higher efficiency across most of the worker counts. So this result highlights that the efficiency decreases as the number of workers exceeds the available CPU resources. Now, let's look at the overall comparison between multiprocessing and multi-threading. So across all of the experiments, multiprocessing consistently outperforms the multi-threading. It achieves lower execution time, higher speed up, and better efficiency in both of the 4-core and 8-core configurations. This shows that the multiprocessing is generally more effective for this image processing workload. And actually, both approaches benefit from increasing the number of workers, but only up to the number of available CPU cores. So once the worker count exceeds the number of physical CPU cores, the multi-threading performance will start to degrade, and the multiprocessing remains more stable and efficient. From the speed-up analysis, we can see that the scalability is limited in the 4-core configuration due to the hardware constraints, while in the 8-core configuration can have higher speed-up. The efficiency results also shows that it is higher when the number of workers matches the number of available CPU cores, and it decreases when too many workers are used. Overall, the 8-core configuration performs better than the 4-core configuration, and the additional CPU cores can be more effectively utilized by the multiprocessing.
Good day, Doctor. My name is Ke Jun. Now I'm going to talk about the discussion of result and insight gains in our project. On this slide, we focus on the scalability of our parallel image processing system. The performance of the system is strongly influenced by two main factors, which is the number of available CPUs cores and how many workers we configure for parallel execution. Our experiments show that the system achieves optimal performance when the number of workers closely matches the number of physical cores. For example, when using 4 cores or 8 cores, execution time decreases noticeably as the worker count increases up to the core count. This demonstrates that the system can scale effectively under moderate parallelism because it efficiently utilizes the available hardware resources. Increasing the cores from 4 to 8 further improves performance, which confirming that the parallel implementation benefits from additional hardware resources. However, once the number of workers exceeds the number of physical cores, performance gains start to diminish, and in some cases, we observe slight degradation. This shows that the system's scalability is fundamentally bounded by hardware capacity. In summary, the system scales well up to the point where the number of workers matches the available CPU cost. But adding more workers beyond these limits does not improve performance and may even reduce it slightly. Even though the system shows good scalability under optimal conditions, there are several bottlenecks that limit further performance improvement. These arise from software constraints, hardware contention, and the presence of sequential operations in the workflow. The first bottleneck is parallel overhead and task management. Parallel execution requires additional work such as process or track creation, task scheduling, synchronization, and result aggregation. As we increase the number of workers, this overhead accumulates and reduces overall efficiency, which causing the performance to stagnate. The second bottleneck is Python's global interpreter lock. Because of the GIL, only one thread can execute Python bytecodes at a time. This significantly limits the speedup achievable by multi-threading, particularly for CPU-bound tasks, which explain why multi-threading performs worse than multiprocessing under high load. The third bottleneck relates to sequential components in the image processing pipeline, such as image loading, pre-processing, and saving. According to Amdahl's law, the serial fractions of the workload limits the maximum speedup achievable, regardless of how many cores we add. This aligns with our observation that speedup eventually plateaus. Finally, we have memory access to cache contention. Operations like Gaussian blur and edge detection require frequent access to neighboring pixel data. When multiple workers execute these operations concurrently, they compete for memory bandwidth and cache resources, reducing cache efficiency and increasing latency. This further limits the benefits of adding more parallel workers. In summary, while the system scales well up to a point, these bottlenecks that I mentioned before explain why we cannot achieve unlimited speedup. In conclusion, this project demonstrates that parallel processing can significantly improve the performance of image processing applications. By applying multi-processing and multi-threading techniques, execution time was reduced compared to single worker execution. The results show that optimal performance is achieved when the number of workers closely matches the available CPU cost. Beyond this point, the performance gains diminish due to increased overhead and resource contention. Among the two approaches, multi-processing proved to be the most effective for CPU-bound image processing tasks. This is mainly because multi-threading in Python is constrained by the global interpreter lock, which limits the true parallel execution. Additionally, scalability is inherently limited by factors such as parallel overhead, sequential operations, and hardware constraints. These observations are consistent with Amdahl's law, which explains why speedup cannot increase indefinitely. Overall, this project highlights the importance of selecting an appropriate parallelization strategy and balancing algorithm design with hardware capabilities to achieve efficient and scalable performance in cloud-based computing environment.